Ledrappier, the second talk today.
Okay, thank you. So where are we? So what I want to do today is finish my first two lectures. And so I want to consider the case of dimension 3. So have a probability measure mu. And there is, I know it's recorded, so there is a hypothesis which I forgot yesterday. So I want to say it now and louder than it erased that I forgot to say yesterday. And the hypothesis, which is very important for us, is mu is as countable support. And why did I forget it yesterday? It's because in our mind, it's not important. I mean, it should be true without that hypothesis, but okay, we can prove only with, with that, and I think it should be clear what the question is on Friday. But okay, all what I said yesterday with that hypothesis. And of course, the hypothesis that you as countable people. Countable. Yeah, I needed to assume that yesterday. For all the results I stated with that hypothesis, which I forgot yesterday. And also the hypothesis I didn't forget, which is that sum of log. Now it's the sum, it's not an interval. Finite. So we are in dimension 3. So we have Oseledets theorem. So we assume, for the sake of today's talk, I mean, it will be another. The results are true also in the other case, but it's another development. No, not sure. I don't think we put it in the paper, but we are realizing that we never use it explicitly. Each time we use it, there is a way around it. So I prefer not to say it, but so we assume that we have three distinct exponents. Okay, let's I recall yesterday, so we know what we have three distinct. So we assume that we have three distinct exponents. T1, T2, T2 equals 0. So the multiplicity are 1 because D1 to D2 to D3 is 3. So we have Oseledets spaces, E1 over omega, E2 over omega, E3 over omega, which are a direction in R. And what we are interested in is the distribution of this direction, which is a point in the projective space, the point in the six-dimensional space. Six-dimensional space. And the first observation we made is that, in fact, there is a nice simplification is that this is the same. To describe this free space, I can describe as well E1 over omega, E1 to 2 over omega. Which I think of it as the unstable flag. And E3 over omega. E2 over the gap was really good. You can think of it as a table. And of course, if I know both, I know E2 by taking the intersection of those two plates. And the observation was that those stable depend on the features, unstable depend on the path, so they are independent. So the measure I want to understand is the product of the two measures. So for the dimension, I may as well look at the unstable path, but I will keep this guy in mind because the main point, the new issue that we want to. So I want we have E1 to E2. That's really the guy we want to. We claim that we know the dimension of. And I said yesterday that okay, we have natural projection. E1 to E2. But they are not, and we know that the dimension is okay here by Rappaport. We know that the dimension of the conditional measure is okay by Pablo last year or 2 years ago also. But that's not enough by what I recall on the first. What is so the new thing is to take another one codimension one vibration, but this one will be random. It will depend on the stable flag. So for each fixed stable flag, I have my three-dimensional space, to have two projections which are natural, and I have a third one, but the third one, which also codimension one, but it will depend on the stable. And what is it? I take E1 plus E3. That's the point. That's the point of the whole lecture. That take a big a deep breath. That's the point. So if I take this this vibration, which depends on E3 and E352, it's codimension one. If I know it, if I know E1 plus E3 to get E1, I just have to one-dimensional direction here. But once I know E1 plus E3, E2 plus E1, and E1, I know E2. And vice versa. I mean, it's codimension one. And this guy is dimension two. E2 is dimension one because E2 belongs to E2 plus E3, which is 6. Normal. So it's dimension one. And E1 plus E3 is dimension one, so it's the direction of E1 in the plane containing E2. So it's the product. It is dimension two. It's simple. It's the product, and the fiber is dimension. So what do we know? What do we know about this guy? Well, the same. I mean, if I but it's codimension one. Codimension one is the function. And it is geometric, so it is equivalent. If I act by G, the stable flag is acted, comes the image gives me the stable flag at sigma omega, but it will give me another stable flag. And the whole picture is completely invariant. So the unstable flag is act of this guy, and I can write a sigma omega, which invariant. And I can and again, like it was here, not only it's equivalent, but when I iterate and let n go to infinity, if I act by xn, essentially it contracts always by the same quantity, which is contraction. And number 2 minus number 1. You have to see it, but it's clear in this system of coordinates, but you are E1. You act, but you can think that E3 is fixed, and E1 goes to E3 with the speed E to the n number T3. Right. In the palette, yeah. Okay, you have to look at it to be convinced, but it's common sense, yeah, especially if you think of it as E3 and determine E1 in terms of E3. So the way E1 goes to E3 is exactly what and you have some entropy scale. Then mutual information of G minus 1 F what guy, the flag. Given. And find the mutual information yesterday. You find in terms of difference of conditional entropy, the strip over all finite. That's why if the entropy is finite, I can write directly the difference of entropy. But if it's not finite, it's still a strip of finite. The difference of entropy for finite conditional entropy of finite. Okay, have all these phenomena, and believe me, F is E1 flag. And the first flag name conditional measure because of all these properties, conditional measure. Okay, what conditional measure of what? I have my omega. All these guys are random, a function of my probability space, the sequence of matrices. So I have a distribution of F. I have a distribution of E1, E1.3 and E2. And of course, the image of the distribution of F is the distribution of E1 to E2. And I have a conditional measure, which depends on the I mean, it's complicated, but it does because it depends on the stable plan. But so R exact image. And the dimension is 2.13 divided by 1. That's the first. So, okay, we are in the same situation as before. We have conditional measure, and the conditional measure has some dimension. It's essentially one-dimensional, so it's the same flavor as what I said on the first day about the counter set. Kappa 1, the entropy. The entropy. It was the visual information of I defined it that time, so it's simple. It has two variables. It will be in fact information of two variables, and it's two over finite partition. So A minus 1 variable F B F variable of the entropy of A equals this guy plus the entropy of B this guy, the same, minus the entropy of space. Is some, the nice thing is that why do we like it in positive? Because it adds up. It's really the difference between the entropy of this section and the entropy of here. So when I have a system of projection like that, this quantity adds up. Because they are defined, they are almost defined. I mean, this is the entropy. There is a log. G minus 1, coordinate, there are two variables, G minus 1 of omega, F of omega. So it is, which is a short way of saying the visual information of sigma algebra generated by G minus 1, the sigma algebra generated by F, conditioned them by the sigma algebra generated by F. Yeah, that's a probabilistic writing sigma algebra by the variable. Okay, so this Pablo will show you because I know that you are eager to see Pablo, but and if I put the model of the thing, tomorrow. Okay, but why do I'm happy with the third projection? All right, yeah. One, that's the entropy. Delta and 3, and there's the dimension. 1, 3, which is and the dimension is I care about the sign, that's why I put P1 minus K2. No, here I'm saying that the contraction along the fiber is K1 minus K2. The fiber is really doesn't see. I mean, that's what I wanted to say. I wanted to forget about it. Why? Because on the space of flag, you have three contractions. You have one K1 minus K3, K3 minus K1, you have K2 minus K1, and you have K3 minus K2. This projection catches the strongest one. And if you look at it, what happens here, on that space, which is random, but still homogeneous and changes in G, the contractions are K2 minus K1 and K3 minus K2. They are smaller. Bigger than negative number, but the contraction is stronger here than in the first. And the second claim in that setting, if the contraction stronger in the fiber than in the quotient, then mention that. When I told you on Monday that if I have a projection, a priori, even if I know that the dimension on the downstairs, the dimension of the fiber, it doesn't add. And the best example are graphs of functions. But I'm saying, what about the graph of function? I mean, the dimension is zero vertically, but the contraction is only lambda. So it's the weakest contraction along the vertical. So we are not, it doesn't add because we are not in that thing. Yeah. Okay. Okay, I don't. This one is T1. Maybe I'm wrong. Each time Pablo, is that correct? Okay. That's I mean, it's three-dimensional. You quote the strongest contraction, so you have this two on the base. But both this number, I mean, this one is the sum of these two. So both these numbers are small. The contraction is weaker on the basis of here. And that's the reason. So that claim, that's the proof from 5x. So if I lose enough time, I will be I will keep it, but that's the key point. In fact, that's what we learned from what we did lifetime long ago. That in dynamics, if you have, I mean, this principle is in dynamics, but still. Okay, so now we are a little happier because we are simplified. We have something which is two-dimensional, and which is not the product. And we can add, and we know that if we understand this, we will understand this one just by adding gamma 1. Okay, but what was that? Here we had the Rappaport result that those guys were exact dimensional. But this one I don't know yet. So I have to prove that this one is exact dimensional also. But it's a product, so I can try to decompose. But there are two ways of decomposing. I can decompose first by projecting on the 153 and then the full 2, or the other way around. So okay, I have two. I mean, it's really in that space, the product I have two projections, very simple. And if you look at it, again, you have the same property. It's co-dimension 1. So the product of two-dimension 1 space is co-dimension 1. It's equivariant because it's completely geometric, defined by the dynamics of Oseledets spaces. And the construction, you can look at it, what it is. So here, chi1 minus chi2. Because you are E2 and you forget about E1. And you go to E2. Here it's chi1 minus chi2, and of course, in the other direction, well, and I can define the entropy. It's the same formula. The difference of entropy has some entropy here. we have some entropy here, which is the entropy of that guy given this one. So the mutual information of E minus 1, E1 plus E2, E1 plus E3, E2, given E2. I don't know the measure is what, so it's complicated. Might be complicated, but it still exists. So I have 3, 1, 2, 0, 1, and 3, 2, 0. So I have the production, I have the entropy, I have the dynamics. The conditional measure here on the fiber, I have a measure here of the projection. The conditional measure on the fiber by one have some dimension, which is gamma 1, 2 here, and gamma 2, 2. Okay, and now I have just one-dimensional thing. A one-dimensional thing I can project. It's not really integral because I still have E3 and E3 to E2 to 3. In the three-dimensional space, you can think of it as in the six-dimensional space, I go to 5, 4, 3, but always have the E2 plus E3 and E3 plus E2, which are there always. So in fact, I can look at and globally it's a product. So I can look at the slice, three-dimensional slice here, but then the foliation is random, and those foliations are depend on which point, which stable point M. But if I look at it, here again, I have so it's one-dimensional, and here it's two-dimensional. Here it's one. I have entropy, so now it's K1 to prime. Not the same. No reason to be the same. Fine. And I have, again, by the first claim, I know that one-dimensional, now it's a projection, in fact, on a one-dimensional random thing. Are exact dimension of fine. Sure, and to have my product space, which is decomposed in two ways into products. So what should I do? But I should use the claim too. I know how to add the dimension. To add the dimension, I want the contraction in the fiber to be stronger than the growth. So I want, for instance, this number to be smaller than this. And I want this contraction between -2 to be stronger than this. Which corresponds. So I want P1 minus P2 to be as close as possible. So this side corresponds to Chi2. No. This side corresponds to Chi2. And because Chi1 to Chi2 plus Chi3 is 0, so the sum of the difference is just the sign. So depending on the sign of Chi2, I know if I want to apply the claim 2, I know which side I have to go. So I start this way. I'm happy because I have the strongest possible contraction. And then if Chi2 is positive, I continue this way, and then I know that I can add a movement. So finally, what's the result? Yeah, it's important. Even the stable flag is important. So you can think of always have the product with stable flag. in the other direction. Each time you have to look at it. I mean, what is what is here? You so you have E1 plus E3, which is given, and also E2 plus E3 is given. That's always given. We'll stay part of the stable class. So you have E3, E2 plus E3, E1. That's given. That's a stable flag. And now I assume that E1 plus E3 is given. And I want to see E2 in that picture. So this guy is codimension 2. But I have two things to determine, E2 and E1. But I want to see E2. Let's go in there. So E2 is here. When I iterate how fast E2 goes to E3, it's by 2 minus. I'm on that plane for E2 plus E3, which is a stable plane E2. And I want to understand how during the action, acting by my product of matrices, how the direction E2 eventually I mean the speed at which the direction coincides towards the one which is the most contracted in that space. And the speed is exactly the difference of the angle. But the angle, I mean, the angle is the coordinate. My one-dimensional coordinate is the angle between the two spaces, between 2 and 3. And when I progress, I go to the most expanded. But anyway, the speed of protraction of the angle is e to the n E2 minus. So that's one picture, and for each picture you look at it, you see what happens with geometric, and you Oh, you have to look at it. It's not very element. It's the same. This one is clear. The other ones are clear when you think of it, but not not improvised. But it's clear. I mean, once you written down, there is no ambiguity. But I mean, each time I want to. So. It's one of the way of things converge to the direction converge to one another. And it mixes the plane of the direction because we are on that. Okay, but now we are happy because we are happy. Because we can add the dimension. So we know given the two planes, we have proven that what again that dimension, the flag space, the unstable flag has some dimension. Right. New F. Flag space has some dimension. And I even some kind of a formula, except the formula. Okay. some dimension. That's my gamma to delta. And delta is what? Gamma 1, 3. It's a sum. It's a sum on the right path. Gamma 1, 3 plus gamma 2, 3 is gamma prime 1, 2 is equal to negative. And gamma 1, 3 plus gamma 1, 2 is gamma prime. So the gamma in the initial formula I said yesterday has some geometric meaning, as the exact dimension of some projection of conditional measure on one-dimensional fiber. But the precise meaning, you have to look at the exponent and choose which order you have to follow in order to add it. And it matters. Pablo tomorrow will show you an example where it's different. I mean, the two results are different. We can compute everything explicitly, and the two results are different. So it matters. Okay, so we have this, and okay, you have to do it, yeah. I'm talking about and yeah, I'll say a word at the end about okay, and moreover, the entropy are much nicer. The entropy they add up anyway, because they are given by integral of log of densities. So the entropy add up anyway. So we know that we get the Fürstenberg entropy on the top is the sum of K1, 2. So both in K1, 2 is and also K1, 2. So the entropy adds up, that's very nice. But the dimension add up if you take them in the right order. That's the conclusion. That's what I wanted to say. Mm-hmm. I have this number. I mean, this number with the entropy here and the entropy. Yeah. This college, when those two are equal, means something, but we don't know exactly what yet. We have a guess. The guess is that if two measures are the same stationary measure, and for at the same our distribution are equivalent, then the exponents are proportional, unless the dimension is two. That's a guess, but we are far from it. But this relation. Okay. Not over. I still have this projection. I mean, I can go from E1 to E2 to E2. I mean, that if I fix to have E1 plus 2, if I fix E3 plus E2, I can go to 2 without knowing this line. And again, it's something which is satisfies all what I read. It's one-dimensional. It's equivariant. And what do you do? Again, it's fixing E3 and choosing E3, E1 on the line going to 3, or no, this one. anyway, if you look at you try to look at it carefully, and you find one minus something here. Because it's new, it's something where I haven't talked about it. If you don't like it, I'm not. So this one was P1, and I project P1 too. I just forget about precise condition of P1, and I just want to remain. What is the line you want? What is the plane you want to? And again, this one here. And I mean, it's a one-dimensional, homogeneous, conformal. There is it's one-dimensional. Conformal. There is some entropy, and first stage of ground again, and you have to find here. Okay. Now, if you give them time 1, 3. Right. Yeah, give double time 1, 3, and another one. I have exact dimension on those fibers again because we claim 1. I erased it, but you are in the same situation. It's homogeneous. There is some contraction. And again, I mean, this guy has the strongest possible contraction. So I can apply my N2 to this factor. And this gives me, I mean, I know already by Rappaport, but in fact, it's true. And this gives me that the dimension of the plane is exact. And the formula is given by some entropy divided by this T2 minus T3, some entropy divided. And the same for the dimension of the project plane. So in fact, I should have said long ago that this was triggered by 2 papers, one by Zheng Feng in for IFS and one by Rappaport in for that case. And which more or less follows the same line. And it was really, I think it was really the idea of Zheng Feng, which already in Feng and Yu for people to know that you can still see vibration on omega, on the space of choices. There are some geometric interpretation, but they are on the space of choices. And you can work with conditional measure on the space of choices and just use the geometry from time to time when you want to use the back density theorem, but not too often. And everything happens on the space of on the probability space, and that okay, that's really when I read the visual paper, oh wow, we can do a lot of things. Okay, so we have the formula. So there's another way of writing this formula, which is Ledrappier. So each K is given by the dimension multiplied by the point. So what we have the floating diagram is given by the 1 minus plus the 1 minus about 2 plus 13 minus 13. T3, where gamma bar is gamma or gamma prime, depending on the sign of the cycle. But I have a nice formula like that. I like that. And okay, so, and also you have the same formula for the entropy on the plane and the entropy of the on the direction. You have same kind of formula. You have this one and this one for the direction, this one like that. And these are different, depending on what. Sometimes it's the same, sometimes it's different. But you have formula for all the partial entropy. You have formula. So you are happy. Yeah. Mu is the measure. What I define as the entropy of the. Mu is a stationary measure on the black space. The level of exponent depends. The level of exponents are defined by Oseledets, even mu I know. I have all these constructions which give me fibers, radiation, measure, and from those I get numbers. And I'm saying that total entropy, because that's the way it came, is given by information in the exponent, given a priori, and these numbers. These numbers, also gamma, are a dimension of measures on one dimensional object. So all the gammas are between them. All the gamma I wrote are all dimension of some measure on something which is one dimensional. So they are all between the exact dimension of measure of one dimensional object. So they are all between zero. And okay, so one more thing I want to say is that from this inequality, you can deduce something which some people in the lab yeah, and I forgot to say that the hypothesis I don't want to state, the support is countable. It's for claim 2. For claim 2, really use it. And we don't know how to it's certainly likely true without it, but there is some little problem. Okay, so I have a measure with countable support. And first moment. And then I have, and I assume that I have 3 experiments. Given this, I can define the what's called the Lyapunov dimension. It depends only on this and the entropy. So I define a function on 0.3, which starts from the entropy at 0. The value at 0 is the entropy, And between 0 and 1, I put the smallest flow. So, the smallest of the differences. So that's the 21 minus 22. 22 minus 22. That's the slope here up to 1. And then I take the other one. Map. And then I take one cloud. Up to 3 if you want. And the Lyapunov dimension is that point here, where that function crosses the exact. Lyapunov dimension of mu. And why does it cross the axis? It's because it's written here. The entropy is smaller than gamma 1 T1 minus T3 plus T1 minus T2 plus T2 minus T2. So the entropy minus the sum of the three is non-positive. Is non-positive. It's the math of the two numbers, T1 minus T2 and T2 minus. I always have to decide which one is bigger and which one is smaller. That's the Lyapunov dimension of u. Yeah, it depends only on u. I have the exponent, I have the entropy. I mean the entropy. Okay. As the entropy of the Oseledets measure. Mu as a compatible support. And the finite moment. I have the Oseledets square. So I know the number. And I know the T1, T3, and I have some distribution on the flag space. I have a Furstenberg entropy for this distribution, which is some number. I start with that number. For length 1, I go with the smallest possible slope, and then a little bigger slope, and finally the slope. And since all the gammas are between 0 and 1, I'm sure that at some point, this curve will cut the stack. So, the entropy is at most the sum of the three. The sum of the three. And le corollary of this formula is delta. Why? Because what is delta? Delta is the sum of the of some gamma. So I have got one gamma which corresponds to K1 minus K2. So if I start here, I can go up down up to gamma 1, 2. So the bar one, so the good one. I don't know which one is the good one. Assume it. No, the smallest one is that one. Here is 2, 3, and here is that one. So I have my formula over there. So I have here a gamma bar 1, 2, which is smaller than 1. So that's some contribution to the entropy. I have another contribution to the entropy, which is gamma bar 3 multiplied by this, which will be that by another contribution to the entropy. And finally, the final contribution to the entropy is divided by gamma 1 3 multiplied by K1. The entropy is the sum of these three quantities, which means, and each one is smaller than 1, which means that this number is to the right, to the left of this. So, and this number is the sum of the dimensions. So, and that's mostly what I wanted to say, except that all the picture is all in the whole dimension. So what do I have to do? So in general, don't you have again one. Have a decomposition in subspaces of dimension d1 dn, and we want to draw the same picture, but now with n guide instead of and the right way of thinking of it, combinatorial, and the right combinatorial is given by, we look at the T, which is the topology on the one n, which is finer than the topology which makes zero. Zero is 1 n, 2 n, 2 n. So that's a topology. Topology on the finite set, intersection of two sets. So it's a topology. And I look at all the topology on 1-to-1, which are final. And if you and so this picture is exactly that. Here I have the topology. So topology can be defined on by atoms. I are the same here, but in general, a topology, if I know the atom, I know the topology for the union of atoms. And here, what do I have? I have initially have the finest topology. Point, atoms are points, photons are photons. And here, what do I do? E1, so I have E1 and E3. So I put together here 1, 2, 2. Here 1, 2. I think and so on. What? And here, eventually, we have the topology of the whole contain, which is 1, 2, 3. 3. So in between here, you have 1, 2, 3. Something. So here we have one. We have add. Yeah. One have to be final and 1, 3. 1, 2, 3. And here have to be final and 1, 1, 2, and 3. I mean, that just to convince you that the combinatorics of this can be described as a set of topologies. And now, if you have a topology, you can say the topology is finer than another one. So it's finer. And it's finer with step 1. If you have just one atom, we change it by adding only one. And that's what we did. We changed one atom by adding 3. No, that's not what we did. Okay. Almost what we did. Forget. And the combinatorics of this guy is exactly the picture that we want. And for each arrow, we have to claim one which applies, but now it's conformal because here it can be higher dimensional. The description is more complicated, but it's a square like this. But you have the same plane, which are still true. And Pablo will explain that tomorrow.
Any comments or questions? So let's thank François again. 10 minutes. 10.